Hello everyone, my name is Subrata Samanta and I am from IIT Kanpur. So I am your tutor for the physics subject. So Gauss law provides you to either way calculate the electric field when you consider the surface have a symmetry, right? So that is called the Gaussian surface. So we will discuss more about this in this class, okay, and some applications of the Gauss law. Basically, we apply the Gauss law in case of first, let us say, apply to the infinitely charged plane, okay, sheet, okay. So you calculate the electric field due to a uniformly charged infinite plane sheet, okay. So yeah, so infinite plane sheet, infinite plane sheet. So basically if we consider a plane sheet, this one, right, plane sheet, okay, and the surface charge density of this sheet is sigma. This is becomes surface charge density of the sheet, and if we draw an axis, so let us say this one is x axis, and so let us say this one is x axis and this one is a y axis and this one is z axis. So it placed in the yz plane, right. So this one the uniformly charged infinite plane sheet, uniformly charged infinite plane sheet. This one is a 2D surface that placed in the yz plane, placed in the yz plane and have a uniform surface charge density is sigma, right. Now we calculate the electric field due to this charge distributions. So we consider a Gaussian surface. So in this case we choose a Gaussian surface, basically this thing. So on the x axis, okay, so the either way we can draw this, either we can understand by drawing this in this way, that basically looks like the surface. So you consider a surface that passing through the through this plane, charged plane, okay, perpendicular, and in the x in the x cap, okay, and this one is placed the y cap and this is the z cap. So basically consider a Gaussian. So here the Gaussian surface, Gaussian surface rectangular parallel pivot. So rectangular parallel pivot of cross sectional area A, okay, and this rectangular pipette parallel pipette placed along the x axis, okay. So along x cap, okay. So you can also consider a cylindrical surface instead of rectangular parallel pivot along x cap, okay. So that is not important for a particular surface. So you can choose any symmetrical surface, that is called the Gaussian surface, that's become easier to calculate the electric field. So now, if we calculate the charge enclosed by the closed surface, so what is the charge enclosed by the closed surface? Charge, so first we calculate the charge enclosed by the closed surface, okay. So the closed surface is rectangular parallel pipette, okay. So this is a 3D surface and this one is closed, it's like a cylinder that we considered in the previous class. So yeah, so what is the charge enclosed by this? Sigma times the area, okay. So area of this parallel pipette A, okay, because the total area of this parallel pipette is A. Second one, we calculate the net flux through the Gaussian surface. So here we consider the Gaussian surface is a rectangular parallel pipette. So what is the net flux? Net flux through the Gaussian surface. So EA, so there is two sides, okay. So one is the along x cap, one is the opposite to x cap, okay. So it's like a cylinder, right? So in case of cylinder, we consider there is a three surface, right? So one is left side, one is the right side, another is a circular part, right? So here if we consider rectangular parallel pipette, so there is also left side and right side, and there is a circular part, it's not a circular but a surface part, okay. The electric flux for the surface part becomes vanishes, okay, and the left side and right side we add, so this is EA and times minus EA, right. So total electric flux in this case is not 0 but is 2 times EA, okay. There is a not 0 because in this case the charge, the electric field above the surface is pointing outwards and electric field below the surface is pointing downwards, right. So there is a extra minus sign, and that gives a plus sign, so it gives, and we add up the total flux, okay. Now we use the Gauss law, so using Gauss law, 2 EA total flux, basically sigma A, the total charge enclosed by the surface, by epsilon naught, so E sigma over 2 epsilon naught, right. So this is the magnitude of the electric field due to a infinitely charged plane, okay. And the vectorially, so if we, because since the electric field is a vector, so sigma over 2 epsilon naught n cap. So in the above plane it's pointing upward, in the below of the plane is pointing downwards, okay. So in the easy way to calculate the electric field of a charged plane using Gauss law. So the similar way, if we calculate the electric field due to a uniformly charged thin spherical cell, so charged spherical cell. So we consider a surface thin spherical cell, okay. So the inner radius r, okay. So basically the radius is r, I consider a spherical cell, the surface charge density of this thin spherical cell becomes sigma and uniform, okay. So sigma be the uniform surface charge density of a thin spherical cell, okay, of radius R. So, in this situation we choose a Gaussian surface as a sphere, okay, and consider the Gaussian surface as a spherically symmetric, right. So, we choose a Gaussian surface to calculate the electric field above the, I think, outside the spherical cell. So, that means we consider the Gaussian surface. So, we calculate the electric field in this point, let us say P, due to this charge distributions. So, we consider another spherical surface, okay, passing through this point. So, basically this distance r, and we consider this one is a Gaussian surface, Gaussian surface, okay, and that is a sphere. Now, we calculate the two things again. So, first is charge enclosed by the surface, Gaussian surface. So, what is the charge enclosed by the Gaussian surface? So, charge enclosed by Gaussian surface is sigma times, so what is the charge enclosed by the Gaussian surface? You just integrate 0 to r, right, and sigma times ds, sorry, yeah. So, basically, yeah, so sigma times the area integral, right. So, the double integral 0 to r and theta is 0 to pi, or phi is 0 to 2 pi, and so sigma r dr d phi. So, this is becomes 4 pi r square sigma, right, because from r to, so from r to small r, right, from this distance to this distance there is a no charge density, right. So, this becomes so there is in this case the sigma is 0, right. So, this gives a 0. So, in that region there is a no charge distribution, right. So, the total charge q, it's up to r, okay, and times sigma, okay. And what is the area and the flux through the surface, Gaussian surface? The second one is the flux. So, flux through the Gaussian surface H. So, E times the electric field times the area of this surface, right, 4 pi r square. So, because since the radius of the Gaussian surface is r, small r, not capital R, right. So, therefore, the electric field, so using Gauss law, so E times 4 pi r square becomes sigma over sigma times 4 pi capital R square over epsilon naught, right. So, this is the total charge q over epsilon naught. So, the E, the electric field becomes q over 4 pi epsilon naught mod yeah, so q over 4 pi epsilon naught r square, small r square, right. And that is you know already, right, that the electric field for a point charge with the total charge q at a point r is q over 4 pi epsilon naught r square, where q is the total charge, right. So, where q is the total charge, sigma times 4 pi r square. So, this one is basically looks like a point charge, whole charge distribution looks like a point charge with a total charge q, that is sigma times 4 pi r square, okay, and we calculate the electric field at any point p at distance r, this becomes q over 4 pi r square, right. That is expected and also calculated from the Gauss law. So, now the interesting point that if you calculate a electric field within the spherical cell, right. So, if you calculate the electric field in that point p, right. So, we draw another diagram. So, if we calculate the electric field, let us say this one is a spherical cell, right, and the radius is r. So, we calculate the electric field let us say here, at a distance r from the center. So again we consider a Gaussian surface passing through this point, okay, and in this case again the Gaussian surface becomes a spherically symmetric, okay, and consider a sphere to be Gaussian surface. So case 2. So similarly, so we calculate the charge enclosed by the surface. So charge enclosed by the surface is, so in this case 0, okay, since the all the charge, okay, are distributed over a surface, okay. So if we consider a small surface, I think if we consider a surface which radius is smaller than capital R, so there is a no charge content within the surface, right. So therefore the charge enclosed by the surface, Gaussian surface, is 0 in this case, okay. So therefore the electric field E becomes 0. Okay. So therefore the final results is that, so E is 0 if R less than R, capital R, and E is 1 over 4 pi epsilon naught q over r square if R greater than capital R, right. This is the form of the electric field due to a spherical cell, where q is the total charge sigma times 4 pi r square. So in this way we calculate the r dependence of the electric field using Gauss law, and by convention and by physical argument we say that the directions of the electric field, right. So in this case, if the q is positive, then it radially outwards, if q is negative, it radially inwards, right. So the directions put by hand, okay, by physical arguments, okay, and the magnitudes is calculated using the Gauss law, okay. So thank you.